It's an extreme pleasure to welcome Eileen Meyer, who is an assistant professor at the University of Maryland in Baltimore County. And she previously worked at the Space Telescope Science Institute and has done a huge amount of work on multi-wavelength data and is particularly interested in high energy astrophysics, and particularly extragalactic radio jets. And I'm very excited to hear this talk, which is about making movies with Hubble and the VLA. So I hope you have your popcorn ready.
Yes.
Over to you, Eileen.
Thank you. So yes, this is work that I've been doing since I was a postdoc actually at the Space Telescope Science Institute, but more recently advancements have been coming from two of my students, my PhD students at UMBC. So I just wanted to particularly highlight Agniva Roy-Chowdhury, who is actually, I think, watching this talk. So he can actually answer questions, and Adam Leah Harvey, who has done a lot of the work on the HST side. Agniva has been particularly focused on some really innovative stuff with the Very Large Array. So to get started, I'm going to start at, actually, Sarah, can you see the title of the slide? Is it blocked by the menu?
No, it's fine. I see it.
Okay, good. It's blocked on my screen, as long as you can see it. So I just wanted to start with a kind of a primer and reminder of, the scales that we're talking about here. I realize everybody here is, an astronomy student, but so, a parsec is about the distance between stars. In most galaxies, we're talking scales of 10 to 100 kiloparsecs. And a megaparsec is kind of on the scale of typical galaxy separations. So what I'm going to be talking about today are these jets from black holes that are on particularly the kiloparsec scale. We say that because they're anywhere from hundreds of parsecs to even as long as a megaparsec. So these are enormous structures that come from the very centers of active galaxies. And I just wanted to, for a minute here, point out, their sort of size scale in reference to sort of these galaxies. The local universe is usually taken as everything within about a redshift of 0.1. That's useful for what we're talking about today, because that's a distance of about 400 megaparsecs. Today I'm going to be talking about proper motions, which are motions on the sky that you literally track over, human timescales. And we can do this for nearby objects on the kiloparsec scale. On smaller scales with the technique using very long baseline interferometry, which I'll bring up again, you can go a bit further. But in general, it's easier to see things move when they're closer to you, right? So there's that kind of relation. So going big picture for a minute, the big question that we're all interested in is how galaxies, evolved to produce the universe that we observe today. We see normal spiral galaxies. We also see active galaxies, like this is Sen-A. This is an optical image with radio and X-ray, and you can see that the black hole at the center is active and it's spewing out these radio jets. And the question is, what is the role of AGNs or of mergers, like that shown at top right, in basically shaping how galaxies evolve through time? And we know that the active galaxy phase is very important. We know that it has major impacts on the host galaxy, on the star formation. It even, things like outflows and jets can heat the intercluster medium. They can offset cooling flows, things like that. So these are big scales. These are some of the, biggest scales that we're interested in as astronomers. And jets are playing a role there, and they're actually still fairly poorly understood. So this is an optical image of a very famous nearby jet known as M87. So I like to use this one to just kind of give you the anatomy of what we're talking about in terms of jets. So the supermassive black hole is down here at this very bright center, which is also sometimes called the core. That black hole will be anywhere from 1 million to 10 billion times the mass of the sun. It's actively accreting material. And at about 10% of AGNs, these active accreting black holes, we get these jets, these highly collimated outflows of relativistic plasma. So when I say relativistic plasma, that means not only are the particles in the jet highly relativistic with Lorentz factors up to, say, 10 to the 6, but that plasma is itself having a bulk motion with Lorentz factors on the order of 2 to 50. Okay, so the relativistic plasma is going to give you what's known as synchrotron radiation, which is why we know these as radio jets. The bulk relativistic motion is going to give you Doppler boosting, and that's what makes them so bright, and that's why jets, especially when they're aligned towards us very strongly, which is what's called a blazar, they can be seen to extremely high redshifts, up to redshifts 5 and 6. So these jets are basically big energy recycling machines, right? So stuff is, the engine is on extremely small scales. We're talking like a solar system type scale. The accretion disk, is a few hundredths of a parsec maybe, and yet these outflows can go well outside their host galaxy, and that can lead to significant host galaxy and intergalactic medium impacts. So that's kind of the big picture impetus. I haven't explained yet why we're interested in proper motions in particular. So jets are generated on very small scales, very close to the black hole, sub-parsec scales. And there's been a long period of observations with extremely high resolution radio observatories to track the motion of the plasma coming out of that black hole on those sub-parsec to parsec scales. And from that, we've seen that these jets that's how we know that they have these high Lorentz factors, which I'll explain. I've got a few slides kind of giving some of the basic equations here in a second, okay? So these images that I'm showing here are not on those small scales. These are large scale jets. So sometimes we use the phrase large scale jet, sometimes we say kiloparsec scale jet. What we basically mean is the jet after that initial very bright base of the jet close to the black hole. It's sometimes called the core or the blazar core. Now we're looking at what happens to the plasma as it keeps going. And it turns out that we actually know a lot more about the plasma at the base of the jet than we do on the large scales. There are many things we don't actually know that well about jets. We don't know the plasma content. So we think, the sort of standard leptonic model is that you have electrons and positrons in the jet. But it's possible that we actually have relativistic protons, and that's a completely different class of models, hadronic models. There's a lot of different radiation mechanisms that can arise depending on the exact plasma conditions under hadronic model. And we actually haven't really been able to distinguish for sure which model is correct. The radiation mechanism is actually unknown. That's another whole line of work that I and my students work on. But these jets give us X-rays and on kiloparsec scales, and we actually aren't really sure how those X-rays arise. We're still very interested in how jets are launched, right? So we know that it's only a fraction of AGNs. We haven't quite really found, the slam dunk, here's the thing that makes an active black hole give you a jet or not. And this is the question that we're interested in here, which is the speeds of the jet. So it turns out that the speed of the jet gives you a lot of interesting constraints, including the total energetics. It can also give you evidence for or against different emission mechanisms. And so it's quite important to map the full kinematic profile of the jet, which so far we have not really been able to do. So here, this hopefully will appear as, hopefully will appear as a little movie. So this is one of these very high resolution radio observations of M87. So this is a jet. This is the blazar core. So now we're way down, zoomed in by the black hole. And you can actually see sorry, it's hard for me to restart the slide to replay it. You can actually see that this is on a matter of days, right? That you can actually see the plasma flowing out of the black hole. So there's a long, long history of tracking these plasma motions with very long baseline interferometry. And it turns out that jets appear to still be accelerating in a lot of cases on these scales. And that's one of the things that motivated us to start looking at what's happening on even larger scales, which is going to require us to completely change the kind of observatory we use. And I'm going to talk about how we can use HST and the very large array in particular. So I haven't yet explained what I mean by superluminal motions or how that can arise. So the top little figure here is a kind of classic diagram of how superluminal motion works. So what you see as an observer is you see little plasma components moving, and you literally just take their position, angular position, and you do the calculation to see how many parsecs per year it moved, and you can easily get numbers that are larger than c. This doesn't mean that we violated the speed of light. It's actually essentially an optical illusion. And the geometry is shown pretty well here. So right, we're on Earth. We're looking at a source, which is down here by this 0, and a blob is emitted. So the blob at first is down by the source, and it emits light, which is this sort of bottom track here. And that light, of course, is moving at the speed of light. In the same time that that light has moved this distance, the blob itself is moving very close to the speed of light. So essentially the blob catches up to its own radiation, if you want to think of it that way. And because this angle theta is less than 90, you can find that this apparent position of the blob moves faster than the speed of light, although this is really just a projection effect. So the actual speeds that these plasma blobs have can be very relativistic. They can be 99% or 99.99% speed of light, but they are not exceeding c, which is a common misconception among the public when we do, videos and public outreach stuff about this. So no, we haven't violated the speed of light. It turns out though that this projection effect, this optical illusion, is quite useful. So from this, first of all, we have the basic observation that speeds from jets on these VLBI scales range up to, here I say 50 C. There's actually been a couple that are even higher, but that's kind of the top end. And that's how we know that the bulk motion has a maximum Lorentz factor of probably about 50, which I quoted before. It turns out if you take your apparent speed, you can directly equate that to your minimum gamma. Okay. So here's a little bit of some basic relativistic physics sort of lesson. So you get interesting physical constraints. So hopefully those of you that had some relativity remember this equation for the Lorentz factor. Beta here is your apparent speed in units of c. So this plot shows the apparent speed in units of c versus angle for a variety of different Lorentz factors kind of typical of these sorts of jets. And one of the things you'll see is that, for a gamma of 15, right, that's this bright pink, the maximum beta apparent that you'll see is 15. So there's that 1-to-1 correlation. Also interesting, if you measure, I think that's on the next slide. Yes, this slide shows that the maximum value is equal to gamma. If you measure beta apparent, and that's this equation here, by the way, which you can work out from the geometry I showed on the previous slide. So if you make a measurement of, let's say, 13C proper motions, it turns out that the only viable curves that you could be on all have gamma greater than 13. So that means that as soon as you measure beta apparent, you have a lower limit on your Lorentz factor. So because Doppler boosting, how bright the source appears, is degenerate as far as the speed and the angle, these are very useful constraints, because we have a hard time directly measuring the gamma or the orientation angle of a jet. So the other thing you'll notice that you get is if you take the limit of the true speed being just 1c, then that gives you a maximum angle for the orientation of your jet, which is also very, very useful. You can also kind of get a lower limit on theta by assuming that the jet is not infinitely long, right? So you say, I don't think the jet is in real life longer than a megaparsec, and that'll give you a not very constraining lower limit as well. Now, I mentioned that it's hard. So these are both constraints, but they're upper limits on theta and lower limit on gamma. But you can actually solve the whole thing. I don't have the equation on this slide, but we did this recently for a source known as M84. So this is a radio jet where you can see one side is a little bit brighter than the other. That top side is slightly more oriented towards us. And so with the the smaller angle of orientation, we get more Doppler boosting. It appears a little brighter. So this jet we can already see is kind of in the plane of the sky. It must be pretty misaligned. So jets that are more aligned, we can't see the counter jet at all because the light is beamed away. In this particular case, what we call the jet to counter jet, so the jet that's going the other way, ratio is pretty low. It's actually 1.4 plus or minus 0.2. So it turns out that the brightness of the jet coming towards you and the jet going away, that ratio also has a path in the sort of theta beta plane that I'm showing here. So what we did for this source is we took this curve, which unfortunately I really should have written the equation for you guys, but there's an equation that gives you the ratio of fluxes relative to the speed and the angle. And you get this curve, and then this red curve comes from our constraints on the speed that we measured from just proper motions. And you can find out where these two curves cross, right, plus rather large error bars. And you can see that the best fit orientation angle for this is about 70 degrees, which is kind of what you would expect just looking at this thing, that you can see the counterjet. It's clearly fairly plane of the sky type source. So that's just a neat demonstration of what you can do with proper motions. So for the next little bit of the talk, I'm going to talk about proper motions with the Hubble Space Telescope in particular. So this is work that we started doing at Space Telescope, and as far as I know, there's really nobody else in the world doing this kind of stuff, which is it's a little unusual. There's a whole proper motions group at Space Telescope, and they were all mentioned on the first slide. It's a team of people that's really been working on high precision astrometry, which is very careful alignment and measurement of position. But most of the topics they're interested in are very nearby to the Milky Way. So maybe measuring the speed of Andromeda or globular clusters, or nearby stars. They can look at high proper motion stars, things like that. Looking at sources that have a significant redshift is a little unusual. So that again is particular to jets because they are relativistic and because they appear to have superluminal motion. So the three jets that I'm going to talk about in a little more detail are M87, 3C264, and 3C273. And I will actually just skip the rest of this slide. So when I say that we're going to use HST, first of all, I think you have had a few talks on radio jets recently. So, you're well aware that there's synchrotron radiation from jets, and that produces a lot of radio emission, which is what distinguishes a Radio-Loud AGN from a radio quiet that doesn't have a jet. But on the kiloparsec scale, what's interesting is that a lot of these jets also show optical emission. So that means that these particles that are radiating have quite high energies, quite high Lorentz factors to give us this optical emission. And a lot of times, generally speaking, the optical morphology traces the radio morphology. And this is just 3 examples of different kinds of jets. So the top one is 3C273. This is the extremely bright object at left is the base of the jet. That's a really powerful quasar. And you can see that the jet extends out and it's actually invisible for some period, and then boom, all of a sudden you have this little train of knots. Looks much the same in radio. M87, that's the one that I showed in the previous slide. So here we have a much less powerful jet. This is orders of magnitude less powerful than 3C273, but we still see the optical emission. You'll notice the difference in scales. 3C273 is on tens of kiloparsec scales. M87 is about a kiloparsec. I include another source that we discovered a couple of years ago that has radio or optical emission called 4C0058 that's actually curved and is similarly on kiloparsec scales. So I also give the distance to these sources because these are sources that are within this kind of proper motions sphere of about 400, 500 megaparsecs, where we can hope to have the accuracy to actually measure the plasma motion. So why do I say it's 400 to 500 megaparsecs? So with HST, the whole idea of doing proper motions requires repeated imaging, of course, to actually track the motions. So we're reliant on programs that were conducted back in the 90s. So these first optical jet detections were done with a now defunct detector called WFIRST. It's actually sitting here in the museum in DC. And you can see that the images I'm showing you on this page are not going to look nearly as nice as the 3rd and 4th generation detector images that we were able to get later. But these images are critical because they give us the 20-year time baselines that we need to track the motions. So while very long baseline interferometry is very high resolution, and therefore they can usually conduct studies over months to years, we really need like 10 and 20-year time baselines to be able to do this work. So it's really, it's almost multi-generational type work. In some cases, there's observing programs that I've started that maybe we'll finally have a conclusion when I'm close to retiring. I did want to mention that two of my mentors, Bill Sparks and John Beretta, actually were heavily involved in these early programs. So here's the rough math. With HST, we could, let's say, be confident in tracking the position of something to about 1/10 of a pixel. In some cases, we can actually do better, but that's a good conservative estimate. So that's 5 milliarcseconds over 20 years. That gives you 1C accuracy at a distance of about 240 megaparsecs. So that's kind of what's setting our scale. It turns out that we can actually do shifts even better than that because we have such high cadence observations in some cases. But that's roughly what sets our, this ability to resolve a shift is really what sets how far away we can observe these motions. So the first study, this is one that was done a few years ago. So is of M87. So this is a nearby giant elliptical galaxy that hosts an extremely famous optical jet that was actually first observed over 100 years ago from the ground. Here I've actually subtracted all of the galaxy light. So what you are seeing, these are not stars, these are globular clusters in the M87 galaxy. This is an HST image. And I've kind of turned up the brightness so that you can really appreciate these globular clusters and how nice and point-like they are. Those globular clusters, there was something like 400 that we could detect. Those ended up being our reference frame. So we took images of M87 taken over 15 years. And we actually just use those globular clusters as little reference point to line up all the images. So we were able to get registration accuracies of 0.17 milliarcseconds, which is really, really good. And so by doing that, we were able to make these movies. So I kind of jumped to the movie part just because I think it's interesting. So you'll notice the date is flowing by at the bottom. We start in 95, going up to 2008. And you can definitely see by eye components in the jet that are moving, that are fading, that are getting brighter. And all of that is super interesting physics. M87 is a treasure trove for looking at jet physics because it's so nearby and we can see in such incredible detail. I'm going to show you a couple of zoomed in movies. This one's going a little faster. Hopefully this is actually showing okay on everyone's screens all over the world. But here you can very clearly see plasma moving through a stable feature. We think that this is some kind of recollimation shock in the jet. This is the outer part of the jet where you can see things have slowed down, but you can still see an outward migration of plasma. You can see that this giant knot A, which is actually the brightest part of the jet, is fading over time. That's consistent with synchrotron cooling. And it's also consistent with the fact that these optical emission is coming from particles that had to have been accelerated in situ. They couldn't have been accelerated down by the black hole because their cooling time is too short. So it makes sense that there's some kind of perhaps oblique shock feature here that's accelerating the particles, they're radiating and then cooling, and we see that fading. This study was important, but not the first actually. So I should mention that there was a previous HST Proper Motion study of M87 published by John Beretta, who was someone I worked with at Space Telescope. My update to this was done in 2013, and now my graduate student, Adam Leah Harvey, is working on another sort of order of magnitude update. What was special about the M87 study was just that it had been observed so many times. This here on the left is showing the position of this component here, dWest, over time along the jet and transverse to the jet. So we were able to see things like this was best fit with a second order term so that we can see that it's actually decelerating over time. And similarly, we were able to see transverse motion for the first time. And in fact, in this paper, this work, we saw hints of what we thought were helical motion. So that would be plasma components that are basically moving along a helical path. And there's been a long, sort of theoretical history of thinking that these jets have, to some extent, helical structure due to their magnetic fields. And we were seeing something that seemed to align with that. Adam Leah's work is even more exciting along those lines, although I don't have a lot of slides from their work yet because I don't want to give too much away. But there's, I'll show just one thing that they've been doing. So we've actually been, not only do we have more data since the 2013 study, we've gone now up to 2018, so another 10 years of data. We've also started using wavelet decomposition methods to actually track the individual features in the jet over these more than 20 years now. And this image here, actually, these little black points are showing components that have been tracked over different epochs. And you can see that they leave little trails, and that the trails are not just going all smoothly outward, right? So there's a ton of interesting velocity structure here. We can see a lot of transverse motions here in this oblique shock feature, which is not terribly surprising. Here, this component actually is the part with the fastest speeds. There's probably some kind of rarefaction happening here, and so the plasma is able to move faster. So there's a lot of really interesting, sort of microphysics going on. One thing I like about this diagram is you can see a couple of globular clusters here, where you can see that the little black component dots are just stacked on top of each other. So those are nice tests that we are actually measuring motions very accurately. The globular clusters are not moving on human timescales. So M87 is a very special jet, and I don't know how many more cases I'll get to talk about, but even if I only talk about M87, it's our best case. This is now a plot of the proper motion apparent speed in units of c versus log projected distance from the core in parsecs. So this diagram shows the accumulated work of several teams working on just this source. And you can see that the VLBA data traces a jet which is seemingly slow until it starts accelerating in this sort of acceleration zone from 10 to 100 parsecs. And then the VLBA capabilities kind of don't go beyond that. And so we have to switch to HST and VLA to track motions on the 100 to 1,000 parsec scale. And you can see that actually the highest speeds achieved are measured by HST at about 100 parsecs. So this is telling us that in M87 at least, the acceleration zone of the jet is very long. It's hundreds of parsecs, especially if you take into account projection effects. These distances are foreshortened since the jet is pointed towards us. And then we see something that looks like a kind of, what we call an envelope. So there's a deceleration happening, over a fairly short distance of, a couple hundred parsecs, so that the outer jet is back down to proper motion of 0. What's interesting is you'll notice those stationary standing shock features that recur in the jet. So I think this here is HST1, which is a well-known stationary feature that kind of rocks back and forth as plasma goes through it. This here is knot D, which we found to be stationary. The leading edge, this was another knot that we found to be stationary. And that's something that we're finding also to be the case in Adam Leah's update to the proper motion measurements. I will move a little bit more quickly through the other two HST studies that we've done that are out in the literature. So this is a famous source known as 3C264. This is what the host galaxy looks like before you subtract the light. If you rescale it so that you can really see the dust disk in the inner part, you can see that there is this really bright optical jet sticking out. If you subtract all the other light components, then you get just the jet alone, which is this figure at the bottom right. So this source is 5 times further away than M87, so our images look a little pixelated, right? So this is, we aren't able to see it as quite high resolution as M87. Here, the black hole is on the left where the little cross is, and the plasma is going out, moving out to the right. And so in 1994, you can clearly identify 1, 2, 3, 4 knots in the jet. And we were very surprised to see that this second knot is moving very rapidly over the 20-year study. And in fact, the third knot is also moving, although not as rapidly. And these two knots end up colliding with each other. So you end up with knot B, which was moving at about 7c, running into the one ahead of it, which was moving at about 2c. And we saw significant brightening of the jet. We've since published an update on this source, and you can see that with further monitoring, this collision zone is getting even brighter. And this was published in 2015, and we were very excited about this because it was the first time we saw evidence of an uneven speed flow in the jet leading to collisions of this type, leading to particle acceleration, which we see as this enhanced emission. So that, what I just described, and this is, by the way, the PR video, which we can now watch. So this is the video of the plasma moving out and colliding with the third knot. So what we get from this is, first of all, the efficiency of conversion during this what we call internal shock collision. So this collision of a slow-moving component that was emitted prior to a faster component and basically an uneven speed distribution was one of the things that was proposed as a way to do particle acceleration in jets. So this figure is now identical in scale to the one I showed you earlier for M87. So we have the apparent speed versus distance. And the gray data is all the M87 data. And the red data points are the slightly fewer data points that we have for 3C264. But what's interesting is we see a stationary knot A, which is very similar to the stationary knot HST1 and M87. And then boom, we see this very fast speed of about 7c, almost at the same distance as we saw the peak in M87. And then we see a pretty rapid deceleration after that. And so it looks like something that's kind of consistent. So we're seeing something, again, where there's an acceleration zone that extends out as far as 100 parsecs. There's stationary features, which might be recollimation shocks, et cetera. So 3C264 was an important study because it validated this idea of an internal shock model for particle acceleration, which was proposed way back in the 70s. So it's not new. It's been proposed as a means of particle acceleration in gamma ray bursts, X-ray binaries, as well as jetted AGNs. And the main thing that it requires at its sort of physical base is an unsteady flow. Now, very quickly, I will talk about 3C273. So this is the third study that we've got out in the literature. And for this one, if you remember that slide I showed of the 3 different jets, this is the one that's almost 500 megaparsecs from us. It's really at the raggedy edge of what we can do in terms of precision astrometry and tracking motions. One of the things that made this very challenging was that in M87 and 3C264, the galaxies are so nearby, we can see the globular clusters in those elliptical galaxies. For 3C273, we can't even see the host galaxy. It's buried under all this quasar light. So we have to use something else as our registration system. And fortunately, in even the early images, there's a lot of background galaxies around the jet of 3C273. Here I've boxed some of them, okay? So we had to come up with some pretty interesting methods to do cross-correlation, basically position matching, especially because, as I mentioned, the 3rd and 4th generation detectors like ACS are a lot better than the short exposure observations with WFIRST that we have from the early days. So this is just a direct comparison of those two. But we were able to get pretty good image alignment, not nearly as good as the M87 study, but 5 milliarcseconds. And that means that the errors on the proper motions that we're looking at are about 1.4c for this particular study. So this is not going to allow us to see teeny tiny little motions, on the subluminal scale. But the reason we were interested in this jet is that it gives us X-ray emission. And one of the potential mechanisms for that X-ray emission required fast bulk motion, like 10c. So 1.4c is not sounding super great if you think your speeds are slow, but if you think you have 10c, 10 plus or minus 1 is fine. So, we were excited to do this study, and then we were kind of disappointed because this is the jet in 95, this is the jet in 2003, this is the jet in 2014, and absolutely nothing moved. The only thing, in fact, that moved was this little point source here, which turns out to be a star. Okay, we saw that moving quite well, which was gratifying that we measured something, but it wasn't the jet. So there was no apparent motions or even a flux change. There was not any sign of any change. And so with a speed limit of less than 2c, this actually ruled out the ICCMB X-ray model for the X-ray emission from these jets. So that was a neat example of how a null result still got us something scientifically useful. This is just a slightly different plot of apparent speed versus distance. I think one of the reasons why we didn't see proper motions is simply that 3C273 is a jet on a much larger scale than the others we've looked at. The others are known as FR1s, which are kind of lower power, more compact jets. 3C273 is 32 kiloparsecs long, right? So while it does have very high proper motions on the VLBI scale, as shown here, notice that there's a big scale break here in the middle of the plot. You know, out here, on much larger distances, kiloparsec scale, I think the jet has already decelerated, essentially. So what's next? We're still working on the remaining jets that were first observed in the 90s with HST. These are all challenging for different reasons, but we are starting to get some results. One of them, 3C78, I will talk about a little more. In the future, where can we go with this work? So in the optical, HST is by far the best instrument, and we've actually started doing some prospective studies of new optical jets that we've recently discovered. It's going to take a few years to get the enough time baselines to make the measurements, but because the 4th generation detectors are so much better, better sensitivity, lower background, we can actually do a study in, let's say, 6 years, comparable to the accuracy we would need like 20 years before. If you want to stick to a similar waveband, of course, you could follow up a jet with James Webb or WFIRST. Synchrotron emission is very broad, and so we don't expect major changes between optical and infrared. People have asked me frequently if we could do this from the ground. Yes and no. If you have a very bright jet, or if you're looking at something that's very far outside the host galaxy, then yes. Adaptive optics does offer you the resolution to probably do this. The sensitivity is more of an issue. These jets are very faint, so it would probably only work for a few cases, very large, bright, hotspots or things like that. However, there is the possibility of, from the ground, looking at a completely different waveband, which is either radio or submillimeter, which is what I'm going to spend the last 5 minutes talking about. So moving into the radio band, this was an idea that came about because we realized we were running out of jets that we could do with HST, even for the few cases we might be able to do a prospective study, simply because we just don't have the long time baselines. The Very Large Array, of course, is a famous radio telescope in New Mexico that's been in operation since the 70s. And even better, jets have those very bright compact cores, so they're used as calibrators, which means that there are jets that have been observed hundreds of times over decades. So although there are some downsides to going down in frequency, namely the plasma tends to not be quite so compact, there are also some major advantages, in particular, just simply the magnitude of archival data. The feasibility of this was already shown, in fact, by the very first proper motion study of M87, which was done with the VLA by John Beretta. So currently, we actually have an NSF project to use archival and new VLA data to track proper motions. So I'm going to give a little update of that. This is all work done by my student Agniva Roy Chaudhary. So one interesting thing, this is just a visual sort of display of the catalog, the availability of archival data. So this is, at left is a picture of NGC 315. That's a very nearby source, as you can see from the redshift. And right, this is a sort of schematic diagram of all the data in the VLA archive at these different frequencies, generally speaking at the highest resolution, so A configuration or perhaps B configuration at the high frequencies. Over time, and the big bubbles here just mean that it's a deep observation as opposed to the smaller bubbles that are shallower. So you can see that a source like this has been observed dozens and dozens of times quite deeply over a time range spanning more than 30 years. And so there are similar plots that we made for all kinds of nearby radio jets. You can see them below. Some of them are really heavily monitored. And so this was the impetus for doing this project. So one of the major challenge here is that nobody else has really done this work. There's been previous, of course, radio proper motion studies with very long baseline interferometry, which is similarly using interferometric data. But here we have some differences from that very high resolution data. Namely, we tend not to have quite the high frequency cadence of observations. Secondly, we're trying to make measurements over 20, 30 years, but the jet scale is simply larger. So we need to get really accurate positions because just simply the physical scale has changed in order to get comparable 1C or less accuracy. So Agnieszka has been doing a ton of heroic work, basically testing different techniques, and eventually found that the best way to do the position measurements is, first of all, to do model fitting in the UV plane, for those of you that have done some interferometry type work. So that's sometimes known as the aperture plane, but it's basically where you're looking at the visibilities per baseline rather than actually at the reconstructed image. And there's major advantages to working in that plane. And also we were doing something known as closure phase fitting, which basically just really reduces the errors from instrumental and atmospheric effects to the maximum degree. So I don't want to talk too much about the techniques, although I'm happy to answer questions about it. So this is one of the jets that we worked on heavily. So this is 3C78, which interestingly enough is also one of our optical jets. And you can see that there's 2 knots in particular that we're tracking over time. This one has 4 epochs. So these are the results that we have currently. So knot 1 is moving at a fairly low speed, 0.3 C. Fortunately, we were able to get very, very nice high accuracy on these measurements. And we even see also a transverse motion of this knot of about 0.14 C. I think as we continue doing these studies in optical and radio that we're going to see transverse motions being very common. And I think that that's probably related back to helical structure in the jet, which has also been seen, I should mention, in VLBI studies. Here's one thing that came up interesting in 3C78. Although the first knot seems to be moving, although very slowly, the second knot did something very odd, which is that it moved backwards. And we spent a ton of time trying to figure out if we had done something wrong. And it turns out that this is real. So the knot seems to have moved backwards. And since the last epoch in 2005, the second to last, it seems to have, kind of started moving out again. This isn't so implausible as it sounds. And that's because when we're tracking these, apparent motions, we have to be careful that what we're seeing is really bulk motion, right? So it's very possible for variability in the jet, right? If it were sort of just arranged just so to mimic motion when in fact there was no motion at all. It's also possible for something like the following story, which we think is also happening in HST1 and M87, which is that you have a standing shock feature, right, which maybe is the result of a recollimation shock, and you see plasma moving out, it fades, right, and new plasma comes into that standing shock feature and brightens. And so depending on your cadence, you might see something that appears to move backwards, sometimes known as the Christmas tree effect. So we're still thinking about this as we were writing the paper, but I don't think that this is just simply, an incorrect measurement. I think it's likely the real thing that happened, and we'll probably see more of these as well. So I'm going to skip this slide because it's a little bit technical, but it's just a few details if anybody happens to ask. The last thing I'll mention is just that we're not the only group doing proper motions of jets. Obviously, there's a huge team of people all over the world doing VLBI. And there's even people who are doing proper motions in the X-rays. This is a study of a very nearby jet known as Centaurus A, which you can't actually see in the optical because it's so obscured. But it has this beautiful, beautiful X-ray jet, which is full of all these interesting little clumpy features. And we can only see these because the jet is so nearby. And so I was tangentially involved in this work that was led by Brad Sneos. But you'll see again this same plot where we compare to M87. And again, we see very slow speeds with VLBI on those scales. We're unfortunately kind of missing perhaps the peak acceleration zone in this jet. And with VLA and with Chandra, we just see rather slow speeds. So I think the big question for our work coming up is, we're still basically putting together the sample of jets with kiloparsec-scale motions. So I mentioned in my last comment here that we have 5: SEN-A, M87, 3C73, 3C264, 3C78, which hasn't even been published yet. And our group hopes to grow this to several dozen in the next few years, and then we'll be able to understand, is M87 a totally prototypical case, or is it a complete weirdo and nothing else is like M87? I think that's the question that we want to answer. So I'll leave it there and take questions.
Thank you so much. That was such an interesting talk. Thank you. I actually have a couple of questions in the chat window. The first one came to me by direct message. That was from Metric, who asks, can you comment on what you think the mechanism responsible for the jet is?
Right. So, we know that you need an accreting black hole. You need an active galaxy to produce them. So it's probably to some extent related to the accretion disk. Now there's, if you go into the literature, there's these 2 famous papers by Blanford, the Blanford-Snayak model, the Blanford-Payne model. One uses tapping more the spin energy of the black hole, if we think the black hole is highly spinning. The other one taps more the energy of the accretion disk. And we know that the magnetic field is critical. So it's kind of like we've got all the ingredients there, but we're not quite at the point of putting in, it all completely together and saying for sure this is the one thing that produces the jet. But we kind of know what's involved. It's for sure these are highly magnetized plasmas. That's very important. There's, if you don't have that high magnetic field, then you don't get a jet. Possibly a standard accretion disk is not necessarily needed, because we see jets from lots of black holes that don't have these, sort of standard thin disk, bright accretion disks. So they're accreting at actually pretty low rates. So that's why we think they might more be tapping the spin energy. But it's a great question. We're still working it out.
Great. And the next question was from Hamid, who asks, can you comment on the potential improvements in your data if these sources are similarly observed with the SKA?
Yeah, SKA could be fantastic, actually, for this kind of work. And I think there's one thing that if I go back a slide, I think there's a lot of interesting work to be done actually in between the 2 scales. That's illustrated very well by this plot. And sometimes I call that the mesoscale. So I think SKA could actually do really well in getting us very, very accurate measurements in this, what may turn out to be kind of the critical acceleration zone, actually, if this turns out to be the common thing, that jets are still accelerating on up to 100 parsecs. I don't know yet, we haven't done enough studies to know if this is something that just happens in the lower power jets or if this is going to be universal. But I think SK could definitely be useful.
Cool. And a follow-up question from Hamid is, in your earlier case, where a 0.7 Z blob appeared to collide with a 0.2 Z blob, is it possible that the true speeds are different, perhaps caused by an effect similar to how superluminal motion comes about?
Yeah, the true speeds, so from that you get that, the gamma must be at least 7. Putting aside any effect like a totally perverse arrangement of subcomponents that, like just happen to brighten and dim at exactly the right way to make an apparent motion, it's possible that they are faster than a Lorentz vector of 7. So you have that ambiguity still. You still just have the lower limit. But I think it's unlikely for this to be, let's say, actually a very slow moving jet. That would not really work with the data we have. I'm not sure if I answered the question quite fully, but yeah.
Okay. I've got a few questions myself. I'll just give a couple of moments pause. Are there any questions from the students in the audience? Might like to unmute themselves. well, if you're thinking, I'll ask my first question, which was it's really interesting to see how the plasma is like moving over these knots. So what are the knots made of, and why don't they disintegrate?
So they're probably magnetically confined, right, to some extent. When you said moving over, did you mean like these weird stationary features?
So there's a nice video showing kind of like a wispiness, that kind of motion,
probably
but the brightness kind of stays still.
Yeah, that was probably not D, which is a little ways back. Let me go to that. This is one of my favorite movies that I ever made, because it's just like so clear that what you're seeing is plasma moving through some kind of structure here. So a long open question, which is sadly still somewhat open, is what are the knots? So in any image where you just, especially don't have the proper motions, you just have a static image, you always have to ask, is this like a little ballistic blob that's moving, right? Which is what, if I go up and back again, which is what some of these look like this little wispy thing that disappears. That looks like a little, packet of something that's moving and cooling with a pretty typical synchrotron timescale. But whatever is going on at the front part here is clearly not the same. So some of these are basically shock features. So that's probably a combination of, the way the magnetic field is aligned, possibly the interaction of the pressure in the jet with the ambient pressure, is causing that feature. And so some knots are probably shocks where plasma might come in not radiating in the optical, for example. It may not have that energy. As it goes through the shock, it gets energized, produces optical emission at that shock, and then pretty rapidly fades. And so in those cases, you might not see motion. So one of the possibilities that we have to consider for like 3C273 that doesn't change over time is, what if none of those knots are actually little ballistic blobs, but they are shock features, and the plasma is moving through it, and those features just don't change. And so it's one of those things that I wish I had a better way to distinguish, because the only thing we can say is, well, if we see it moving, it's got to at least have that speed. But it's assuming that we have a good cadence to really convince ourselves we're not being fooled. But it is hard sometimes to be sure.
Cool. And a follow-up question, well, slightly connected, I guess, is back at your other slide where you were showing the peak brightness. I just found it very interesting that you had MA27 and 3C264 appearing to coincide. Do those two AGN have similar mass black holes?
Yes, they're both very massive, which is kind of what you would that's what you would expect for nearby FR1s. We kind of have a sense that these are highly evolved systems. They've been accreting for a long time. So they have like 10 to the 9 solar mass black holes, kind of typical for them. They actually have quite similar like structure, the way you look at them. 3C264 is a little bit shorter, but if it just had a couple more knots, it would be like a dead ringer for M87 basically. And they both have this stationary knot right at 100 parsecs. So they share a lot of similarities. Their spectral energy distributions are a little different in the jet. The M87 is a bit lower energy, and I think it's probably a little bit more misaligned, which actually goes along with the fact that it has slightly lower speeds. So, but they're kind of like sister jets.
Okay, so I was wondering if you could use that as like a characteristic. Maybe if it's probably harder. It's probably harder to measure the base, that knot, to that precision than it is to measure the black hole mass. And
yes, yeah. They're both actually really difficult. And one of the things that it's very boring, so I don't talk about much of the technical details in these kinds of talks, but this is actually technically very difficult work, both the HST side and the interferometry side. It's quite challenging to get the alignments that you want, and then to just double check every potential source of error so that you really are sure that you've made the measurement.
Very, very cool. Thank you so much for talking to us about proper motions of jets. Final round of applause to our guest speaker. Please unmute and join me.
Thank you.
Thank thank you very much again.
Okay. See you guys.
I'll stop recording now.